In this example, we're going to look at the enhancement nmos device again, but this time it's going to be discharging as opposed to the previous example whenever it was charging a capacitor. So if we take the example here, let's say we've got the gate sitting at 0 volts, we've got this side here sitting at 0 volts, and we've got a capacitor which is already charged up to 5 volts. So comparing this to the previous one, the capacitor was originally sitting at 0 volts and we charged the capacitor up. But this time the capacitor's already got 5 volts on it, and we're going to discharge that capacitor through the transistor. So first of all, we have to work out what side is our source and what side is our drain. Well, it's an nmos device, so if it's an nmos device, then electrons are the charge carriers. Electrons travel from a low voltage side to the high voltage side, so the low voltage side is the source and the high voltage side is the drain. So this is going to be the source and this is going to be the drain. So we can write that down here as well. So that's the source and that's the drain. So then we can use our equations in order to work out what's happening with this device. So in this instance here, we've got the enhancement nmos, so it's going to be Vt is equal to 1 volt, and we're interested in the VGS minus Vt. So VGS is, well, the gate is 0 and the source is 0, so VGS is 0 minus 0, and the Vt is a value of 1. So it's going to be 0 minus 1, which is minus 1. So our VGS minus Vt is minus 1, so that's less than 0. So VGS minus Vt is less than 0. So this device here at the moment is cut off. So there's no current flowing in this device. It's just a static device with these voltage levels. Now let's see what happens whenever we go on to this example here. We'll maintain this 0 volts here in the source, but we'll allow the gate voltage now to rise to 5 volts. So whenever the gate voltage rises to 5 volts, it turns on this transistor and there's a current flow in the transistor. And what happens is this capacitor will discharge through the transistor, and we're interested to work out what's going to happen to this drain voltage. So the drain voltage was at 5 volts and we want to find out what that drain voltage goes to and the currents that are going to flow in the transistor. So again, we can use our equations here. We've got our VGS. Well, our gate source now is going to be 5 minus the 0, which is a 5 volts. So VGS minus Vt is 5 minus 1, which is 4 volts. Now again, we want to compare our VGS minus Vt with our VDS. Now our VDS is going to be the drain voltage minus the source voltage. Well, the source voltage is 0 and the drain voltage is, well, we don't know what the drain voltage is, so we'll just leave that and we'll just call it the VD. So the VDS is going to be Vd minus 0, which is just Vd. So now we've got our VGS minus Vt and we've got our VDS, we can then make the comparisons. So if the VGS minus Vt is less than or equal to 0, then it's cut off. But the VGS minus Vt is 4. So we're really saying that if 4 is less than or equal to 0, it's cut off. Well, 4 is greater than 0, so it is not cut off. So there is current flowing in this device. So then we can check and find out whether the current is a linear current or whether it's a saturation current. So we know that if VGS minus Vt is greater than Vd, greater than or equal to Vd, then we're in the linear region. But we know that VGS minus Vt is 4 and we know our VDS is just the Vd. So we're saying if 4 is greater than or equal to Vd, we're in the linear region. Equivalently, we could just read it backwards. We're saying if Vd is less than or equal to 4 volts, then it's a linear current. Equivalently, we can look at this equation here. We can say that if VGS minus Vt is less than or equal to VDS, then we've got a saturation current. So again, VGS minus Vt is just the 4 and the VDS is just the Vd. So if 4 is less than or equal to Vd, we're in saturation. Equivalently, we just read it from this side over. If the voltage Vd is greater than or equal to 4, then we've got a saturation current. So this really is telling us that whenever the VD is greater than or equal to 4, we've got saturation current. So it starts off at 5 volts and then it discharges. So once it discharges with a saturation current until it gets to 4 volts. Now once it's got to 4 volts, it continues to discharge, but it discharges with a linear current until eventually it's fully discharged to 0 volts. So these are the two currents here. It starts off between 5 volts and 4 volts as a saturation current, and that's the saturation current here, which is beta n upon 2 times a VGS minus VT. Well, VGS minus VT is just 4, so it's 4 squared. So that is equal to beta n upon 8. So this is our saturation current. And then it goes on for the next 4 volts, when it discharges between 4 volts and 0 volts as a linear current, and the linear current is given by this equation here. So this is just our beta n times our 4 times our VGS minus VT, but the VGS minus VT is the value of 4 times the VDS, which is just in this case VD, and again it's the VDS squared upon 2, but of course the source voltage is just 0, so we can just leave that as VD squared upon 2. So it doesn't really matter about the values, I just put them in just as an extra so we can see the actual equations. So the summary on this then here is that the device runs in a saturation current from 5 volts to 4 volts when it's discharging, and then it goes on to the linear current between 4 volts and 0 volts until it's fully discharged. So let's go ahead and we'll look at this again in the simulator, and it'll all become pretty apparent and clear as to how this is working. So again, if you open up the file in the resources section, you'll get access to the simulation. So again, it's an nmos device. So this is the nmos device, and it's got a threshold voltage of 1 volt. Now we'll go in and we'll set up the gate, source and the drain voltages. So originally the gate voltage was sitting at 0 volts and the source voltage was sitting at 0 volts and the drain was sitting at 5 volts. So that's us there. So we've got our gate voltage is 0 volts, drain is 5 volts and the source is 0 volts. So we can see here that there's no current flowing in this device. You can see it's cut off, and because there's no inversion there, you can see this line up here is way up above the channel here, so there's nothing happening in the channel. The device is cut off. Now what we do is we go ahead and we change the gate voltage up to 5 volts, and this will turn the device on. So we put that up to 5 volts. So you can see now when it's sitting up at 5 volts, we're sitting in with a saturation current. So that's the saturation current here, it's in red. And you can see that it is in saturation because we've got a pinch off point here. And it means that the current now, the actual electron flow is flowing along in this direction here out through the drain, but the actual conventional current flows from drain to source. So there would be a capacitor up here at the drain, and it's discharging through the device down through the source to 0 volts. Now what we're interested in is what happens to the drain, because the drain is going to discharge. So let's see what happens if as the drain voltage decreases. So we know it's sitting with a saturation current, and that's what we predicted with our equations. So we can reduce this down, and you can see as we reduce it down, you can see what's happening on the right hand side here. It goes down to 4 volts, and when it gets to 4 volts, it then goes from the saturation current into a linear current, and that's what our equations predicted. Whenever we go down below 4 volts, we can see now the channel exists, the inversion exists all the way along the channel, and you can see it's going to discharge, and it's just going to continue discharging all the way down to 0 volts. and it's going to be fully discharged. So you can see that the device here, the NMOS enhancement, whenever we're charging a capacitor, it will charge up to one threshold voltage below the voltage that they started with. But whenever it's discharging, it'll charge all the way down to 0 volts. Again, these are useful and interesting things to know for when we go and use the devices to actually design some circuits. So we've got 2 more to go, and that'll be us finished with the pass transistors. So thank you for listening. I'll get you in the next video. Goodbye.